Okay, good morning, everyone. Today we are discussing the questions from 16 to 30, the MCQ questions in our evaluation test 2. This is your 16th MCQ. So it's asking variation or change, increasing order of the radii of these 5 ions. Okay, so simply when we discuss about radius lamai, there are two things. Okay, atomic radius and ionic radius, right? Atomic radius and ionic radius. So radius, you have two things, atomic and ionic, right? Atomic and ionic. So under atomic radius, simply we discussed that under three different ways, right? So we have covalent radius, right? Then we have van der Waals radius, and then we have metallic radius. So we get some estimation about the atomic radius using these three different ways. Okay, so there's no way of actually finding what is the distance from nucleus to the outer margin of the atom, because outer margin is not definite, right? I hope you understand that. Then when it comes to ionic radius, it's simply we have two types of ions now. We have anions and we have cations. Anions are negative ions and cations are positive ions. So there are some very basic things related to these two ionic radii. Example, anionic radius is always larger than the neutral atom. So let's say we can, if you put an example, O2 minus will always be greater than oxygen atom's radius. Okay, it should be. Why? Because there are more electrons, you can see, in oxide ion. So those electrons are repelling from each other. Okay, due to electron repulsion, the radius of that ion will get larger. Okay, so opposite happens for the cations. Cationic radius is smaller than the neutral atom. And for example, if you take sodium, sodium plus is smaller than sodium. Okay, the opposite happens here because now you have fewer electrons than the neutral atom. Okay, so those fewer electrons are well attracted to the nucleus. Therefore, the size of this sodium plus is smaller than sodium. Right, like that. Just have a small explanation along with you, because along with this, because sometimes they can use this for MCQs. I mean, not this. They can ask reasons why this is happening. So in that case, you need to have some idea regarding this explanation idea. Okay, so I hope it is clear, not that difficult. It's simply about why anions are larger and why cations are smaller. Okay, right. Then when it comes to this now, you have in the periodic table, right? And if you take this oxide ion, it has 10 electrons. Okay, and if you take the sodium ion, it also has 10 electrons. So both these entities, sodium plus and O2 minus, are having same number of electrons, right? And there is another theory in this ionic radius called isoelectronic ions. Isoelectronic ions. So what are isoelectronic ions? Right, simply as I said, the ions that are having same number of electrons. Okay, so oxide and sodium ion are isoelectronic ions. Understood? So like that, there is a sequence of isoelectronic ions. You can see the other elements nearby these two are also take part of this series. Understood? So the isoelectronic ions are, we can put like this, N3 minus. Now see, nitrogen is having 7 electrons originally. If you take 3 more electrons, it becomes 10. Okay, so 10 electrons. Then O2 minus, F minus. Then you have sodium plus, magnesium 2 plus. Then aluminum 3 plus. Okay, so these are the, this is the series, right? And what about the radius? Like I said, anions are larger. Now, if you apply the same logic, now N3 minus has a higher negative charge, so more repulsion. So N3 minus should be larger than O2 minus. Okay, like that, you can see this is the way of decreasing radius of these entities. So in that MCQ we are looking, it is checking this single theory. Understood that? Okay. So as you review, you have to understand where this part is coming from. So ionic radius is coming from the topic under radius. Okay, and then when you are studying, you have to look about these theories also. So what is covalent radius? How it is defined? Then look how this van der Waals radius is defined. Then you have to compare what is larger for a given atom, van der Waals radius or the covalent radius is larger. Like that, you have to compare. Okay, so study those theory points also. Right now, they will be clearly there in your note. In case if you have forgotten these things, right, then you can always go to the recording and revise them. Okay, right. Now let's go and find our answer. Right now, look at the 5 answers. So the smallest one should be Al3 plus, isn't it? And there's only one answer that starts from Al3 plus, isn't it? There's only one answer. So that answer is answer 2. Answer 2. So it's too obvious. I think you can't miss this one actually. Right? Still, if you got it wrong, so please study and remember it's not a difficult part. Okay. So Al3 plus, Mg2 plus, F minus, O2 minus, and N3 minus. That is the ascending order, increasing order of this radius. Okay. So remember what is the main theory point? If you recall again, the theory point you have to remind quickly is isoelectronic series. Right. I hope that is clear. Then let's move into the 17th MCQ. 17th MCQ, right? In 17th MCQ, it is asking the number of moles of K2Cr2O7 potassium dichromate needed to oxidize 1 mole of sodium oxalate Na2C2O4. Right? Now, kind of get used to these names. It will be better, right? In acidic medium. So now you can see it is a redox reaction, and it is given the unbalanced skeleton of the reaction is given. Now it is telling a dichromate is reacting with oxalate to form chromium ion and carbon dioxide. So that's the reaction that is happening. Now you have to know the products now in order to start balancing the redox reaction. Right now it is also given. Right, but when you go to the A-level exam, mostly they are not giving you the products. Okay, so by then you will be done with inorganic chemistry. So once you do inorganic chemistry, like I mentioned in the class, the products will not be given. Okay, so just remember that point. So until that, when we are giving papers, we will give you the reaction. And so, however, so it's asking you to balance this one. You need to find how many moles of potassium dichromate is needed to react with 1 mole of sodium oxalate. Okay, so let's balance this one and then come to this question they are asking, right? So I remind you quickly about redox balancing here. It is a new theory that you are learning under A levels. Let's try to recall that one. Now, the iron is KCr2O7 2 minus. Now you are omitting potassium from this equation. Why? Because potassium is not take part in the redox reaction. So it's just an observer. Okay, so or we say spectator ion. So when you notice such ions, just ignore them and start balancing. That's the way. So don't put potassium or sodium into this equation. Okay. Yeah, one of your friend is asking, how do we identify this to balance using redox or inspection? So if you about to balance using inspection method, Lamai, you will be given all the reactants and all the products. That's how you identify. Okay, and with the practice, you will notice this is actually must be a redox reaction because dichromate, oxalate, they are involved in redox reactions. With the practice, you will gather that. But anyway, so to balance using inspection method, you must be known the all reactants and all products exactly. But in this reaction, you will notice when we balance, there will be H plus is added, acidic medium, and there will be water molecules added. So those are not given in that equation. So you are not supposed to balance that one with inspection. Understood? Okay, so just have some idea, right? Later, when you are with the practice, you will exactly identify it. But right now, just remember oxalate dichromata, they are in redox reactions. Okay, that is enough. Now, we all did S block, remember, last few days. When we are doing S block, those reactions, we know exactly the reactants and products. For example, when sodium is added to water, you know that it is producing sodium hydroxide and H2. Now you know the reactants and products exactly. Then you don't need the redox method. You can balance that one using inspection. Understood? But here you don't know where the water comes from in this reaction. You don't know where the H plus comes from. So then you must go with this redox method. Understood? I hope it is clear. Now that's a good question actually. Now let's come back to this balancing. Okay. So our reactants are potassium dichromate, and we omitted the potassium thing, and then oxalate C2O4 2 minus, and those are reacting to form chromium 3 plus and carbon dioxide. Right? If you recall the method, the process for balancing, the very first thing we must do is what? Balancing the atoms. Okay, so I'll write them here in case you want to revise them. So first step is steps. So first step is balancing the atoms. Balancing the atoms. So for example, if there are two chromium ions, the dichromate thing, you need to write 2Cr3 plus. This is what is meant by balancing the atoms. Okay. So the very first thing you must do, put 2 in front of this one because you have two chromium ions in the left side. And you can see now you must do the same thing for carbon also, because here you have carbon 2 atoms and here you have only one. So put 2 in front of this. Now you might wonder, why don't we do anything for oxygen, right? So the reason is this. We are balancing the atoms here of redox element. Redox element. Redox element means the element that undergo oxidation or reduction. Understood? Now, if you carefully look at this equation, you will understand the oxidation number of all oxygen atoms are -2. Oxidation number always it is -2. So oxidation number is not changed, no. So therefore, don't try to balance oxygen here. It will get automatically balanced at the end of this process. Okay, so you have to only focus about redox element, which are chromium and carbon here. Is that clear? Okay. Now, the second thing we must do is finding oxidation number. Find oxidation number. All these things are nicely noted and, tables and everything they are in your theory tube. So just go look at that one. For the review, you can note down this, okay? So find oxidation number. So what are the oxidation numbers here of chromium and carbon? So for finding this, you have two methods. You can either draw the molecule or iron and get the oxidation number. But for this method, I actually prefer the mathematical method. Remember? So sum of oxidation numbers of each atom is equal to the overall charge. That's the theory. Sum of oxidation numbers is equal to overall charge, right? So oxidation number sum. So how do we get it? So it is chromium. So we don't know the oxidation number of chromium. So let's put that as X. Now there are two chromium atoms now. So you have to say 2X, right? And then oxygen oxidation number is generally -2. So there are 7 oxygen atoms. So -2 into 7. So now we added all oxidation numbers, right? And it must be equal to the charge, like I said. Charge here is -2. Okay, then simplify this one. 2x minus 14 equal -2. Then if you move 14 to the right side, it will simplify it to +12, right? And x will be +6. Like that, this is what we call as the mathematical method. Without the structure, you can find this oxidation number. Okay, it's actually an average oxidation number. It doesn't matter for this equation, this balancing, just get it. Okay, I hope you all remember how to do it. So here the oxidation number is +6, right? And we are not going to stop there. Why? We found X, oxidation number of one chromium atom. But you can see there are two chromium atoms. So we need to find the total oxidation number, or we say in our theory tube, remember, cumulative oxidation number. So what is our cumulative oxidation number? We just have to do multiply this one by 2. So if you multiply this one by 2, you will get plus 12 as the cumulative oxidation number. Understood? Plus 12 as our cumulative oxidation number. Okay. So find oxidation numbers. If necessary, you need to find cumulative. If needed. And here, carbon, if you do the same process, you will find it is +3. Okay, and there are two carbon atoms. So +3 into 2. Oxidation number, cumulative oxidation number is +6. Okay, and here chromium, iron oxidation number will equal to its charge. So it is +3. So it's for one chromium, and there are two chromium atoms in this one. So cumulative will be +6. And here also you can see one carbon atom in carbon dioxide is +4, and there are two carbon. So it is going to be +8. Understood? This is our cumulative oxidation numbers. So what you need to do, first balance the atoms and then find cumulative oxidation numbers. I hope that it is clear for all of you. Yeah, it is very simple. If there are several atoms, you need to find cumulative oxidation numbers. So one of your friend is asking, how should we know whether we need to find cumulative? Right? It's simple. Why? Because if there are two chromium atoms here, then you need to find cumulative. Understood? So now if you take like this SO3 2 minus. Okay, so here's only one sulfur atom is there. So you're not going to find cumulative. So X plus -2 into 3 equal to -2. X minus 6 equal -2. X equal +4. Understood? This is your oxidation number. And when you are balancing this one using such iron, you are not going to find any cumulative because there's only one sulfur. But can you see the difference? Here you have two carbon. Then you need to find cumulative. Okay. Let's do some questions. Let's do some balancings which already we did in class. Right? Go through those examples. Okay, then you will understand it in properly. Okay. Right. And there's another question. Yeah, that is I answered. Right. Okay. Now come to this one. So what are the two steps we completed? We balanced atoms and then we balanced the oxidation numbers. Okay. Right. Now the third step. Now you need to check the change of oxidation number. So you need to find electrons exchanged. Okay, you need to find number of electrons exchanged. Right? Now here you can see chromium is kind of going from +12 to +6. +12 to +6. Now if you put an arrow like this, it is going from +12 to +6. So now in this process, the oxidation number has decreased. Okay, so you can write oxidation number has decreased. If oxidation number is decreasing, right? So what do we call it? It is called as reduction. If oxidation number is decreasing, that is reduction. So we can say this has undergo reduction. Reduction. Write the full word, reduction. So when it is undergoing reduction, it is gaining electrons. So it is gaining electrons. So during this reduction has gained how many electrons? Has gained 6 electrons. Okay, so when chromium atoms are undergoing reduction here, those are gaining how many electrons? 6 electrons in total. Understood? 6 electrons in total. Right, so simply just get the difference. Plus 12 to plus 6. So 6 electrons are gained. Simple. Then look at the other one, carbon. Carbon. Here carbon is undergoing what? Oxidation. Then other one must be oxidation. No argument there, okay? So it is oxidizing from plus 6 to plus 8. Okay, plus 6 to plus 8. This is oxidation. Oxidation. So how many electrons it is gaining? Sorry, during oxidation, electrons are lost. Sorry. So then how many electrons? From plus 6 to plus 8, it is losing 2 electrons. So you can say lost 2 electrons. Now here you can see it is gaining 6 electrons and losing 2 electrons. So it is not balanced, right? So the principle of redox equations is when someone is gaining electrons, other one should lose the same number of electrons. So it's kind of an electron exchange. You can't create electrons. So you can understand now, if this one is undergoing reduction, it is gaining 6 electrons, but this is losing only 2. So it's not balanced. So this needs 6 electrons. So in order to give that 6 electrons, what this must do? This must happen thrice like this, 3 times like this. Understood? So that means for balancing electrons, you need to multiply this one by 3. Then it will give you 6 electrons. That 6 electrons can be accepted here. Is that clear? So when you multiply this one by 3, you need to multiply the entities by the same number. So then here 3 comes in front of the oxalate time. But now here already you have 2 in front of carbon dioxide. So then cut that one and multiply by 6. So it is, 3. Then it will get 6 carbon dioxide. Understood? So electron exchange must be same. Find electron exchange and balance it. So there are proper ways of mentioning these statements in your book. Refer that one. I'm not looking at that one. I'm just going through my memory. So it's fine, right? But when you want to write something, look that note also. Find electron exchange and balance it. Right. Now, this is enough for you to find the answer for the question. Okay, this is enough for you to find the answer for the question. Why? Because now it is telling you, I'll complete the lesson, give me a few minutes, but I'll explain the answer first. Now the question is asking what? We'll see the question once again. It is asking how many moles of potassium dichromate is needed to react with 1 mole of oxalate, 1 mole of sodium oxalate. Now it is showing you this. It's showing you this. Now, if you take potassium dichromate and sodium oxalate according to the part B balanced, you can see the ratio is 1:3. That means what? With 1 stoichiometry ratio, with 1 potassium dichromate, 3 sodium oxalate will be reactive. So 1:3 ratio, 1 mole to 3 mole. With 1 mole of this, there will be 3 moles of sodium oxalate is reactive. But what you need to find is how many moles of this one is reacting with 1 mole of sodium oxide. Right? So simply what you need to do, just divide this one by 3. Right? Divide this one by 3. So it is going to be 0. Or simply 1/3. 1/3 is 0.333. Understood? So let's say 0.33 moles. So that must be our answer. Is that clear? So simply you need to work the ratios and get your answer. Look at the answers. That's the 4th one. This is going to be your answer. Understood now? So we didn't completely balance this. That's what I want to show you. So in some cases, MCQs like this, you can easily find the answer without going through the whole balancing. Because once you get the ratio, this number 3 or whatever, then that's it. Okay. But for essays and structured essays, you can't stop here because it's not completely balanced, right? So if it is an balanced equation, atoms must be balanced, right? And charge must be balanced. Now here, those properties are not completed. So now let's balance the first of all charge. The fourth step is balancing charge, right? So what is the charge, overall charge here? What is the overall charge here? So now, since I wrote so many things here, so now kind of might be confusing, right? Not clear. So I'm going to erase this part, the part we found answer. I hope you wrote down that one. So simply work with the ratio, okay? Now let's put this equation, the partly balanced one, here. Again, dichromate reactive 3 C2O4 2 minus 2 give 2 Cr3 plus and 6 carbon dioxide. This is the one we balanced up to now. So it's not fully balanced. Like I said, we need to balance the charge, right? And look at the charge here in this side. What is the charge? Minus 2. And don't forget this 3. 3 into minus 2. So minus 6 and minus 2, minus 8 charge is there. And in this side, you have no charge here. 2 into 3 plus 6 charge is there. So how do we balance this now? We have in our hand, we have H plus. By adding H plus in the acidic medium, you have H plus. So we need to balance this charge. So adding H plus to the right side will increase the positive charge. It will not help to balance. Get the idea? So if you add, let's say, 2H plus here, so then it will become plus 8. Plus 8 and minus 8 is not the same, no? Right? So don't add H plus to the already positive side. Add it to the lower charge side. That means the other side. So if you add how many electrons? Minus 8 to plus 6. If you draw a number line, you will understand it properly. Minus 8 lies here, plus 6 right somewhere here. So from here to here, how many electrons you must add? You have to add 14 electrons. 6 plus 8, 14. So those, 14 not electrons, 14 hydrogen, right? Those 14 hydrogen you are going to add to the left side. Okay, so then the both side charges will be same. If you check the charges here, it is plus 8. Now this side, plus 6. And the other side charge is also plus 6. Now it is balanced. Understood now? So that's what called as balancing the charge. And our final step is, after doing all these things, you can balance the number of hydrogen atoms. Balance hydrogen. So for that, we are adding water. Now if you check the right side, you don't have any hydrogen. But if you check the left side, you have 14 hydrogen that is newly added. To balance those hydrogen, what we must do? Add water. So water obviously is added here to the other side. And you must add how many water? 7 H2O molecules. So this is the final balancing. And in essay and structured essay questions, you will be given marks for writing the whole full thing. Understand? So if you can take this one in a single line, like this, you will get the full marks in your paper, essay paper also, right? I gave 30 marks for balancing. One essay question, 30 marks. So out of 150, 30 marks were given for just balancing. Just imagine how it is, how much it is important. Okay, so I hope you got a small idea. So kind of reminded the kind of forgotten theories if you want this one, right? So please go through again the theory note. And there are enough recordings and everything. The question papers we did. Now I recommend you to go to the papers because there we have more questions now, right? And our answer, like we discussed, is going to be answer 4. Okay, Lama? Study this one, right? Study this one. It's never too late. It's all about the commitment, how much commitment you put here. So you now understand by now that, no? because your term test and everything is coming up. Now you are writing some exams. Now you are getting ready little by little for the A levels, right? So let's do this, no? We'll see how it goes. Month after month, you will get improved. So everything not happen, it's not going to happen overnight, right? You have to be realistic, no? So do more practice, and after a while, you will feel that you are improving. If you do nothing, then you stay the same, or you might left behind, because others are studying. Right, now let's go to the 18th question. It's about gases. You can do the question here, see the question here. Which of the following statements regarding a sample of an ideal gas is true? Okay, so in earlier discussion, we got an idea about ideal gases. So the gases that are existing in real nature, it is called real gases, the actual gases, right? Real gases. And those, it's very kind of difficult to do calculations for real gases. Okay, so it basically depends with the conditions we use. So therefore, what we do, we define a new hypothetical gas called ideal gases. Ideal gases. Okay, ideal gases. So ideal gases are simply the gases that are having no intermolecular attractions and that are having no particle volume, or simply the volume of particle is neglected when compared to the distance among particles. Okay, so you know these points, right? So all those points are described in kinetic molecular theory, right? So what are the points that are there in kinetic molecular theory? If we just recall, we memorized this one earlier. What is the first point? First point. Yeah, the kinetic molecular theory. First point. Yeah, it's about the tiny small spherical particles. Okay, so gas particles are very tiny and they are small and they are spherical particles. So the words are tiny or small spherical particles. Small spherical particles. So basically the kinetic molecular theory is describing about the nature of these gases, nature of ideal gases. Okay, so here, so there was a long sentence, but this is the part we highlight. Okay, small spherical particles. And then the second thing is what? Volume of particles is neglected when compared to the distance between two particles, or we can say volume is neglected. There are two ways of telling that. I'll write the both ways. Right, so volume of gas molecule is neglected when compared to the distance between two molecules or particles. You can use those words, no problem. Molecules. Okay. And the same thing can be written like this also. Instead of this sentence, we can say the volume of gas molecule is neglected, is negligible when compared to the volume of the container. Volume of the container. So same meaning. Okay, so it's telling you one simple thing. What is that? Ideal gas particles are, this is a very crude sentence. Don't write this one if they ask the kinetic molecular theory. You need to give one of these two statements. So what is the crude way of telling this one? Ideal gas molecules have no volume. Or you can say pointed masses. pointed message. So remember, this is a very crude way. Okay, crude way means what? So it's not very good, right? It's just giving you the idea. Okay, but it's not good to write in an essay or structured paper, right? Just remember. Okay, understood? So those are the two, those are the first two things. So what is the third one in kinetic molecular theory? Third one? Third one is what? Hmm? Yeah, they move in random directions in a random straight line, different speeds. Okay, so random directions in straight line, random straight line in different speeds. So I hope you remember in an MCQ, as I remember MCQ 15, we discussed about these different speeds. So refer that to again, different speeds. So it's basically telling about the movement of gas molecules, right? And the fourth one is about about how they generate pressure. So pressure is given by collisions of particles on the sides of the vessels. Pressure is given by collisions of the gas particles on the sides of vessel, sides of container. Okay. And then the next one, fifth one, is about their attraction forces and the repulsion. So intermolecular attractions and repulsions do not exist. Okay. And one particle moves independently to another. So because there are no attractions or no repulsions, right? And the sixth one, the last one, is what? It's about the average kinetic energy. So average kinetic energy of one gas molecule is directly proportional to absolute temperature. Okay, so like that, here we have the kinetic molecular theory. So refer that note again. If there is anything missing, you can add that here. Okay, so just simple overview. Because you can see the most of the statements given here are related to that theory. Right. Now look at these statements, Lama. So now when you're going through that one, now see whether you can identify the wrong one. So I'll share you a small review that I prepared. You can see this. Which of the following statements regarding a sample of ideal gas is true? Right? Look at the first statement. The velocity of gas molecules do not change due to the collisions. Velocity of gas molecules do not change due to the collision. So it is wrong. So you can understand when gas particles are colliding on the wall, right? When gas particles are colliding on the wall, right? And their speed is not changing, right? But when they collide with one another, their speed might get changed. Okay, so there are two things now, speed and velocity. Now here it is telling about the velocity. Velocity, as you know, it is a vector quantity, right? So I'll explain by drawing this in the board also. Okay, just look at this one. Let's say now this is our content. So if this particle is coming in 5 meters per second, right? So when it is colliding here and bounce back here, right? Its speed is not going to be changed. It is 5 meters per second. But as you can see, since the direction is changed, velocity was changed. So when colliding on the wall of the container, velocity is changing, but speed is not changing, right? And there is another option, colliding with another particle. So now let's say when this is coming 5 meters per second speed, it is colliding with another particle that is heading in that direction or in other direction. In the same way, their paths will be crossed, right? So let's say it is traveling in 2 meters per second speed, right? So then after the collision, their speeds, both speeds may get changed. I can't say must change, they may change. Okay, so when speed are changing, then velocity will also be changing. So like that, collisions of particles with one another, speed and velocity both might get changed. Understood? So those are the possible collisions now. Right? Now look at this question again. So what it is telling? What it is telling? When the velocity of gas molecules do not change. So it's wrong. Velocity is changing in all cases. Right? If I say speed, then it is not changing with collision of the wall. Now you can see these blue color statements. You will understand what I said here. Is that clear, Lama? Any question on that one? Collision thing? It's very understandable, right? So kind of like collisions that you study in physics, right? So will get changed, right? And in all these collisions, okay, in all these collisions, the average kinetic energy is not going to be changed, right? Kinetic energy is not changing. So that also depends. Now, let me explain. So in here, kinetic energy is not going to change because it is colliding with the wall, right? And here, since they are colliding with another particle, so their total kinetic energy remain constant. After the collision and before collision, total kinetic energy is constant. But one particle's kinetic energy may get changed. So now earlier this was having a certain kinetic energy, but after the collision, that energy might get changed. Okay, so like that, think. So these collisions and everything we further explained in our theory note. So please refer that too. Right, but at constant temperature, okay, like the last rule of the kinetic molecular theory is telling you, average kinetic energy remain constant at constant temperature. Okay, average means you consider all the molecules and get an average for by dividing from the number of molecules. Okay, I think that is enough. And look at the second one. At a given temperature, kinetic energy of a molecule is constant. It's wrong. Okay, so it is only the average kinetic energy. So average word is not mentioned. Understood? So you can see within a green color box, I said that average is constant, not just kinetic energy. So some of you might selected this statement. It's wrong. Okay. So you can see the kinetic energy distribution will follow the Boltzmann curve. Okay, so for actually in this lesson, we are drawing the Boltzmann curve for the speed, but energy also follow the same curve, right? So the third one is telling about the Boltzmann curve. So we'll do small discussion about Boltzmann curve here, right? So Boltzmann curve, it is telling it is symmetrical. It is not symmetrical. So that is correct. So it is not going to be symmetrical, right? You saw in our earlier question, Boltzmann curves. Remember in 15th question? So all these Boltzmann curves are not kind of symmetrical, right? It's not going to be symmetrical. So telling that is wrong. Understood? It's not symmetrical. So answer is answer 3. That is the correct one. Okay, that's the correct one. And then refer the fourth statement. When the temperature of a sample increases from 300 to 600, right? 300 to 600, average kinetic energy of molecule becomes double. Okay, so that's wrong, right? Average kinetic energy is not going to be double, right? So 300 to 600 is not the multiplying temperature by 2. So average kinetic energy is referred to, proportional to absolute temperature. So 300 Celsius is not the absolute temperature. You can see the calculation I did here, right? So 300 Celsius is actually 573 Kelvin. Understood? 573 Kelvin. So if you need to double the kinetic energy, average kinetic energy, you need to multiply that 573 by 2. Okay, so then average kinetic energy will be doubled at 11,146 Kelvin. So if you need the Celsius temperature, just subtract 273 from that one, then you will be given 873. Understood? So my point is this one. So the average kinetic energy of 300 Celsius is doubled, not at 600. It will be doubled at 873 Celsius. Okay, you need to do a small calculation and get it. So remember simply, okay, you don't need to do this to select this answer is wrong. Simply remember, average kinetic energy is directly proportional to absolute temperature, not to the Celsius temperature. I hope it is pretty much clear to everyone, right? And look at the last statement. It is telling energy of individual molecules is conserved after collision among them. So it's not individual molecule energy. It is the total energy. Okay, like I explained here, remember? So this molecule, let's say this molecule was having E amount of energy. So after the collision, this is not going to be E. This may be E, but it may also not be E also. But let's say this is E1 and E2, the total energy. So after the collision also, the total kinetic energy will be E1 and E2 total. Okay, but these will have different values. Let's say instead of E1 and E2, let's say this is 10 and 5. So total energy is 15. So after the collision also, total will be 15, but these two will have different values. Maybe 7 and 2. Sorry, 7 and 8, like that. We don't know it. Understood? So kinetic energy of individual molecule may not be preserved. Okay, so you can't say like that. It's not a suitable answer. Total kinetic energy will be preserved. Okay, Lama? Total kinetic energy will be preserved. So remember that one. So it's a good question, right? Good question. Few students ask some doubts also about the question. I remember. But anyway, I hope you understood the method and everything. Just let's do more questions like this. Okay, when we are doing past paper, sorry, your term test papers, we will see more questions like this. And like I mentioned last month, from this month onward, you will be having a test for each month. Okay, so monthly test series will begin from January, right? So imagine how many tests we can do, no, until your exam. So by that you will get better. Don't worry. Okay. Just do what I say. Right. Now let's go to the next question. Next question. 19th question. So it's telling, it's a small chemical calculation question. I saw most of you got troubled here. But anyway, I'm going to explain it fully. Just read the question by taking a minute. Toluene C6H5CH3. So don't worry about the name. Just get the formula. That's what we need. Is oxidized by air under carefully controlled conditions to benzoic acid. Okay, so this compound is oxidized to another compound. Okay, fine. Which is used to prepare food preservative sodium benzoate. So sodium benzoate formula is also given. So don't worry about the names, right? So because you haven't done organic yet, so just stay with the names. This is the formula, sorry. Okay. So what is the percentage yield should be? Okay, fine. Present yield of the reaction that converts 1 kilogram of toluene to 1.21 kilograms of benzoic acid. Okay, so toluene formula is C6H5CH3. So it is finally converting through benzoic acid. It is converted to C6H5COONA. benzoic acid. So, it says CO2 and it is telling 1 kilogram of toluene is used, right? And you got only 1.21 kilograms of sodium benzoate. Oh, so toluene to benzoic acid, ne? Sorry, my mistake. It is benzoic acid. So CH3, C6H5, CO2H. Right? So how many kilograms? 1.21 kilograms. Okay, so it says 1 mole of toluene gives 1 mole of benzoic acid. So that you need for this question. Just remember, if 1 mole reacted, okay, so you'll be given 1 mole of product. So simply their ratio is 1:1. That's what they are telling. So because you don't know the reaction for this one. Okay, so you don't know the reaction. That's why the ratio is given for you. But when it is given for A-level paper, or I gave the same question for 2026 A-level monthly test with you. And for them, I didn't give this statement because they must know how to balance it because they have done organic, right? So like that, you also have to get improved during this time. Okay, so anyway, so 1:1 is the ratio. 1:1 is the ratio. Now let's convert this one into, now it is asking percentage yield. Okay, now let's write something about that too. So percentage yield. This tells you, we discussed these earlier questions too, right? So the amount that you expected mass, right? And then you are putting the actual mass you got. Actual mass of benzoic. Expected mass of benzoic. And then you multiply this one with 100%. This is how you find the percentage yield. Remember, it's just like the way you are getting marks in an test or exam. Out of 100, you get how many marks you get, no? So the same way, 100, the total marks over the expected marks, right? Okay, right. So this one, what we know here, we know the actual mass of benzoate, which is 1.21 kilograms. You know it, right? What you need to find is expected. How many grams that you are expecting? Okay, so here, since you are reacting 1 kilogram, so don't say 1 kilogram is the expected, it's wrong, right? So you are reacting 1 kilogram. So let's find out how many moles of toluene or this compound is there. In order to do that, you need the molar mass. So C6H5CH3. So how do we find the molar mass? Just add the relative atomic masses. So 12, there are 7 carbon atoms, 12 into 7, plus 1 into 8. So 72 plus 8, right? 12 into 5, no, 7 is 84. 84 plus 8, 92. 92 grams per mole. This is the molar mass. Okay. So then find moles of C6H5CH3. That is 1000 or 1 kilogram over 92. So don't simplify. This is the number of moles. And since it is giving 1 mole of, so one of this one give 1 mole of benzoic. So then you can say moles of benzoic. C6H5 CO2H. Moles of benzoic will be the same. That's why the 1:1 is given. Okay, so then you can find expected mass. This is the expected mass. So for that also you need the molar mass, no? Let's find molar mass of benzoic. This one, benzoic acid. So again, there are 7 carbon atoms, 12 into 7 plus 1 into 6, 6 hydrogen atoms and 2 oxygen atoms, 2 into 16. Okay, so 84, 90 and 90 plus 32, 122 grams per mole. Okay, so from this one you can find expected mass of benzoic acid. Expected mass of benzoic acid. What should we do? Just multiply this one by the molar mass. Okay, so 1000 over 92 is the number of moles that we are expecting. Multiply this one by 122. So this is your expected mass in grams. So now let's find out the percentage here using this formula. So percentage here will be equal to the actual mass is 1210 grams. Expected one is 1000 over 1000 into 122 over 92. So this 92 will go above. Let's put 92 here. And then into 100%. Simplify this one. Okay, simplify this one. And then you will get, you can see 121, 122 can be simplified. These zeros also can be cancelled. So almost you will get 92% almost. Is that clear now? That's how you do the question. 1 mole of toluene gives 1 mole of benzoic acid. Toluene molar mass, benzoic molar mass are found. Then toluene moles, expected benzoic acid moles and then grams. Then put it to the formula. So that's why you are not going to cut them earlier. So then it's very difficult to simplify. You can see 121 and 122 is approximately get cancelled. You can use it. Right, let's go to the next one. 20th one. So I'll first of all explain and then show you the review. From the given electron transitions, now these are ABCD questions. That means you may have different answers. I mean A, B, C, D. You have to select. You are familiar with this one by now. So now let's look at the question. From the given electron transitions in the emission spectrum of hydrogen, identify those which belongs to the visible region. Visible region. So it's hydrogen emission spectrum. Right. So I discussed this one several times with you. So now let's see simply how do we get the answer here. In hydrogen spectrum, emission spectrum domain, the single electron of hydrogen atom, first of all, when you supply energy, it will jump to upper energy levels. Okay, so now let's say this is your hydrogen nucleus and these are the energy levels. You know that when the difference of energy levels, energy difference is decreasing. So when the single electron lies here at the ground state, when you supply energy, this can jump to upper energy levels by absorbing energy, right? And then you will get the absorption spectrum. So once you allow this energy to be released, okay, once you allow this energy to be released, it will emit that energy and come back to the lower energy levels. Come back to the lower energy level. So this is your first energy level, second, third, fourth, fifth, like that you can continue. You have infinite energy level up to that, up to infinite energy level. So when these electrons are jumping from upper energy level to lower energy level, they will release the absorbed energy. It's very simple. Absorbed energy is released here, right? And here, uh, since only if you consider one hydrogen atom, it has only one electron, right? But here we are representing all possible transitions. That means we consider a sample of millions, billions of atoms. So now in that sample, all possible transitions may occur, right? So we can represent all possible transitions. So they can jump back to, first from second energy level to first energy level, and then third energy level to first, fourth energy level to first. Like that, it can descend back, right? So I'll draw one more energy level, sixth energy level. Can 6 to 1 also it can jump. Okay, and then it can jump from third to second energy, fourth to second, fifth to and sixth to second. And here also it can jump for third energy level. I think these are the possible transitions that you will get. So these are kind of sections, right? You can see the longer the arrow I draw here in blue color, if it is longer, then that means it is releasing more energy. Okay, so you can understand that. Longer arrow means release more energy. So that means, okay, so these are relevant for the electromagnetic radiations. Energy of electromagnetic radiation, EM radiation, is high. Okay, so if the energy is higher, okay, so this is belonging to the what region? UV region. Okay, so that is found, that is discovered in the UV region. So we call this series as what? Lyman series. Lyman series. Lyman series lies in the UV region, higher energy. Understood? And this is lies in this Balmer series. Balmer series is there in the visible region. So the electrons that are jumping from from upper energy levels to second energy level, not all jumpings, right? Only the first four lines. So these are having colors. This is having red color, green color, blue color, and violet color. RGBV, red, green, blue, violet. Okay, so after, let's say, seventh energy level to second energy level, it is there in the visible, not in the visible region. It is there in it is more having more length now. So will be there in the UV region. And these transitions are belonging to the infrared region. So these are having names also, Paschen, bracket, and fund, like that. You have names. Okay. So now this is simply the emission spectrum. So there's no much big theory behind this. If you can draw these lines and understand what I said related to this energy, that is enough. Okay, and there's one more thing we can do. So this is not actually the one we see. What we see is the kind of a spectrum, right? So that spectrum also we can draw. Right, now you can see higher energies are there in Lyman series. So Lyman series lines will have larger gaps. This is Lyman series. And then Balmer series, there's a small distance between Balmer and Lyman. It's not a small distance, actually they are widely separated. But for the drawing purpose, we will draw them a little bit close by. And their lines will have an even narrower distance, like this. Okay, so this is your Balmer series. Okay, now you can see Balmer series lines are kind of the gap between Balmer series lines are lower. Okay, draw this a little bit away, right? And look at this gap. That same gap is there between the second and third lines of Lyman series. So this is B1, B2, B3, and B4. We have alpha, beta, gamma, delta, like that. Different names are there. Okay, then you have partition like that, even narrower uh, gaps, right? So now what is the increasing direction of energy? This way energy increases, frequency increases, wavelength decreases. So you can see in the direction of increasing frequency, the gap between lines decreases. Like that, you can find several other statements in your theory note. And I'll give you a small activity. Go and refer why this line is thicker. Remember, the first few transitions of each series are kind of very bright, thick, more intense, right? Find the reason. We have discussed these things. But anyway, this is what you need, right? Now let's go to the question and see. So the first transition is 2 to 1. It is in the Lyman series. Like I said, it is in UV region. So B, 3 to 2, it is okay. It's actually red color line. And C is 4 to 2, that is also there in the visible region. Right? And 4 to 3 in the partition series, it is in the infrared region. So answers are B and C, correct answers. Okay, so write a good explanation for that. If the answer is B and C, you can see from the above table, answer is answer 2. That's the answer you need to select. Okay, Lamai? So that is your 20th question. Now let's go and look at this 21st MCQ. Okay, so emission spectrum, I hope it is enough, but study more about that, okay? So 21 is about, oxidation number, and it's a redox reaction. And as you can see, it is balanced. If you check atoms, 2 nitrogen atoms are there in the left side, 2 nitrogen atoms are there in the right side. So this question is asked about that reaction. And mainly it is focused about the oxidation numbers. You can see all the statements are starting by telling oxidation number. Okay, now let's take the reaction here. 2Cn minus reacts with 5OCl minus and 2OH minus. It's happening in the basic medium. It is mentioned in the question also. Alkaline medium. That means basic medium you can write. And 2CO3 2 minus. Yeah, space might not be enough. Give me a second now. 2Cn minus and 5OCl minus and then 2OH minus. Reacts to form 2 carbonate, CO3 2 minus, and N2, and then 5Cl minus and H2O. Okay, so now it's asking about the oxidation numbers now. So now let's come to the board and find all oxidation numbers of all atoms here, right? For some structures, for some atoms, we need their molecule structure, okay? For example, if you start from OH minus, right? So what is the structure of OH minus? This is Lewis structure. Now the negative charge is there on oxygen. So oxygen is generally, oxidation number is -2. Okay. So this hydrogen is +1. This oxygen is -2 oxidation number. So now even though we write it as OH minus, don't misunderstand that H is having negative charge. It is wrong. Okay, in some places we are drawing it like this. This is the proper way. Okay, but when you are writing it, it's okay to write like this. Okay, no issue, because anyone who understand the basics will know this, no? So no problem, right? But in organic chemistry especially, we write this OH minus like this. We try to show where the negative charge is. Okay, so like that one by one we will figure out this one. Okay, so oxidation numbers of one ion is okay. Now let's look at this one. OCl minus. Okay, it's same thing. The negative charge will be there on oxygen, even though it seems like it is there on oxygen, Cl, sorry. Right, and the oxidation number of oxygen here is again -2. Cl oxidation number is +1, because here this is more electronegative, so electrons are pulled toward that direction. So this is losing one electron partially, and this is gaining 2 electrons partially. Okay. Then Cn minus. Cn minus, this is the Lewis structure. A negative charge is there on carbon. Now check. Nitrogen is pulling 3 electrons partially. So oxidation number of nitrogen is -3. Carbon, look at carbon very carefully. This one is gain 1 electron, which is on the negative charge, and lost 3 electrons. So overall oxidation number is what? -2. Okay, so carbon oxidation number is -2. Remember that one. We got that one by drawing the structure. That's it. Okay. -2 and -3. Sorry, not -2, my mistake. +3, +2. Okay, +2. So oxidation number sum should be equal to the charge. No? Check that too. If you add -3 and +2, you will get -1, the charge. So it's correct. Okay. And then look at the right side. Now let's check what are the oxidation numbers of these molecules. First, start from carbon. This is the Lewis structure. Now you can see each oxygen atom is -2 oxidation state, having -2 oxidation state, and carbon atom is having +4 oxidation state. Because here electrons are pulled, 4 electrons are partially lost from carbon. And nitrogen, to draw the molecule, this is it. So electrons are shared between the same atoms. So oxidation number is 0. And Cl minus oxidation number is equal to the charge, -1. Okay, and here you have water, H2O. This is the molecule. And oxygen is more electronegative. So again, oxygen is -2 oxidation number here. Hydrogen is +1 oxidation number. So now we found all the oxidation numbers. Okay, in exam, you need to do this quickly. Okay, so now let's look at the statements. Look at the first statement. Oxidation number of oxygen in OCl minus is changed from 0 to -2. Oxygen, it is -2 always, no? You can see all these ions, molecules are having oxygen in -2 oxidation state. So A is going to be wrong. A is going to be wrong. Isn't it? It's oxygen always here, okay? In this example, here, oxygen always -2. Here, okay? So there are exceptions. For example, hydrogen peroxide, H2O2, remember, oxygen oxidation number is -1. Right? But here, in this question, all oxygen atoms are having -2 oxidation number. Look at the statement B. oxidation number of carbon is changed from +2 to +4. Carbon oxidation number is changing like that, no? Yeah, that is correct. B is correct. Okay, because it is having +2 in Cn minus, it is having +4 in carbonate. C statement, oxidation number of nitrogen is changed from -3 to 0. Nitrogen, yes, -3 to 0. That is also correct. Okay. And the last one, oxidation number of chlorine is changed from +1 to -1. That is also correct. +1 to -1. Now you can see there are many entities undergoing oxidation number changes. We'll talk about that later. I mean, after getting the answer. So, what is the answer anyway? Last 4 statements are correct. Look at this PDF. See, last 4 statements are correct. So, the true statements are another combination BCD. There is no combination here. So, it is any other combination. So, answer is answer 5. Okay, Lama. Answer is answer 5. Now, check this one. Check this one. Now, what are the things that has undergone reduction? Reduction has happened to chlorine. Write this one addition. Reduction happened to chlorine, Cl, and then oxidation. Oxidation has happened to carbon and nitrogen. Nitrogen from -3 to 0. Carbon from +2 to +4. And the other one that undergone reduction is Cl. Oxidation is carbon. So there are 2 entities that are undergoing oxidation. That's the difference in this question, okay? So generally we saw in earlier 18th or 19th question also we saw when we balance, remember, there's only 2 redox elements, carbon and chromium was in that equation. But here there are 2 elements oxidizing and only 1 element undergoing reduction. Okay, so when this one is reducing from +1 to +5, +1 to -1, it is gaining 10 electrons because there are 5 such ions. And here 2 carbon going from +2 to +4 by losing 4 electrons. And nitrogen, 2 nitrogen is going from -3 to 0 by losing 6 electrons. See, total electron exchange is still 10. You can note that too. So they haven't asked such questions, but anyway, if you improve the question, if you make it more advanced, we can ask the questions like this: how many electrons exchange in total? Like that we can ask. So the total electron exchange is 10. 10 is lost by these 2 elements, carbon and nitrogen, and 10 was gained by chlorine element. Okay, so write those statements too. So that is your 21st question. That is okay, I believe. Let's go to the next one, 22. This is actually from a past paper question, 2020, as I remember. It's asking about the given atoms, are they in the same line or are they in the same plane, like that. So we'll get to the structure and discuss the statements. So the given molecule is like this. And they have labeled these atoms P, Q, R, S, T, U, and V. Okay. Now, to start the question, first of all, get the Lewis structure. Get the Lewis structure. Okay. So this is not the Lewis structure. This is just an skeleton that show bonds. So here lone pairs are not represented. Okay. So the very first thing you can do is by adding lone pairs, you can complete this structure. There will be 2 lone pairs attached to the oxygen. Okay. And there will be 2 lone pairs attached to this oxygen. Now it is complete as a Lewis structure. But looking at this, we can't get any answer because this is not the actual arrangement, no, actual geometry. Okay, so we need to apply VSCPR theory, which we have done a great deal in our very first discussion of this paper. We went to in depth and discussed that. Okay, so using VSCPR theory, get the geometry of each atom and draw this one according to that. Then you can easily explain this in an MCQ discussion. So now there are 4 repulsion units around the carbon. So this is tetrahedral. Okay, and here also 4 repulsion units. So tetrahedral electron pair geometry. Okay, and these two are linear. And this is trigonal plane. Like that, we can get the electron pair geometries. Electron pair geometries. But the shape of this one is angular, okay? Okay. So how do we draw this one? This is not the actual arrangement. No? Now, if you just look at the statement, some students are confusing here. They think, okay, they are in the straight line. So this is not the actual arrangement, right? So actual arrangement, we can draw in this way. Let's start from carbon. These two they are in the straight line. Because linear electron pair geometry means 180 bond angle. Okay. So here the other one is the oxygen. And this one is trigonal plane electron pair geometry. So 120 bond angle. Approximately 120. They are changing a little bit, but anyway, approximately 120. Not exactly, okay? Here exactly 180. Then you have lone pairs. The lone pairs are there in the same direction. Don't get that mistake also. Because water molecule is having 104.5 degrees approximately. Because of the lone pairs are locating at the same side. I mean, same side means they are adjacent to each other. And then you have this CH3. That's also tetrahedral. So 109.5 degrees approximately can change, okay? Because oxygen is a different atom. So anyway, my point is here, you can get the structure in this way. So now depending on this structure, decide whether they are in the same line or same plane, right? So the theory is this: if they are in the same plane, you must check sp hybridized atoms, and bonded ones. Then for example, here you can see these two are the sp hybridized atoms and the bonded atoms are these. So these 4 atoms are there in the same line. Same line. Understood? Then same plane. Same plane is like this. If they are in the same plane, sp2 hybridized atoms and bonded atoms. Because trigonal plane is also in the plane. Hybridized atoms and bonded atoms. Okay, so what are the bonded atoms? These atoms. These atoms are there in the same plane. Understood? So in blue color and red color, I mark that for you to understand easily. Okay, so these 4 the red color ones, the circled one are there in the same line. And others are there in the same plane. So additionally to these 4 atoms, these oxygen and hydrogen are also there in the same plane because this is trigonal plane. But this carbon is not there in the same plane because this is tetrahedral. So it can jump away or into the plane. And these hydrogen are also in a different planes. Like that. Okay, now let's go and check the answer. See, atoms labeled P, Q, R, S. P, Q, R, S are the carbon here. Okay. P, Q, R, S lie in the same straight line. It is wrong. So let's label P, Q, R, S also here. This is P. This is Q, R, S, T, U, and V. Okay, so P, Q. P is not in the same line or not even in the same plane. So it's wrong, right? First statement is wrong. Right? Look at the second one. Q, R, S, T in the same straight line. That is correct. That is correct. Because R, S are sp hybridized and T and Q are bonded to that. Third statement. R, S, T, U, V. R, S, T, U, V. R, S carbon, carbon. And the three carbon atoms are R, S, T. UV are the oxygen and hydrogen. Yes. They are in the same plane. Correct. Then the last one. R, S, T, U. U is an oxygen that is with 120 angle to the 120 bond angle. So it's not in the same line. See, it's a good question. It's a past paper. This is the level we need to practice. So answers are again B and C. Answer is answer 2. Hope it is clear, Lamai. Take a good look at this one. Look at this one and study this well. Okay. And practice more questions. There are more questions in your tube. Bond angle, bond length, like that. There are theories. So study that. Okay, now let's move into the next question. Question number 23. 23, and this is the last ABCD question. Yeah, they're asking the correct statement. So there are 4 statements. I'll explain them one by one. Although SO2 and H2S have similar geometrical shapes, their bond angles are not equal. Okay. So let's go to this one, SO2 and H2S. SO2 and H2S. SO2, the Lewis structure is this one. Okay, now you can see there are 3 VSCPR units. There are 3, and 1 lone pair and 2 bond pairs. So then the electron pair geometry is trigonal plane. Sorry, electron pair geometry is trigonal plane, and the shape or the molecular geometry is angular or bent. So this is the name, or V shape sometimes we call it. And H2S is like this, right? And there are 4 VSCPR units, 2 lone pairs and 2 bond pairs. And electron pair geometry is tetrahedral. And shape is again angular or bent. You can see the same name is there, but obviously their angles are going to be different. So this is derived from 120 angle. So here 120 minus 2.5, you can see 117.5 as the bond angle. For this one we can say 109.5 minus 2.5 into 2, because there are 2 lone pairs now. So now the bond angle is approximately 104.5, but here H2S, I think we discussed that under bond angle lesson. It is having a lesser bond angle than water. Water bond angle is 104.5. here the bond angle is 92 degrees. It's pretty much really bond angle was decreased really well because of the higher bond length and lesser electronegativity of sulfur. Bond angle has decreased. So that's another topic. You need to think about why this is happening. Why it is not 120, 104. Why it is not 104.5. Check the reason. Okay, check the bond angle theory part. So now look at the question again. Look at the question again. It's telling, although SO2 and H2S has the same geometrical shapes. Yes, geometrical shapes are SO2 trigonal planar, H2, angular, and H2S is also angular. Both are angular. Their bond angles are not equal. That is correct. So statement A is correct. Okay, look at the next statement. The electronegativity of carbon in CF4 is greater than the electronegativity of carbon in CCl4. CF4 and CCl4. So it's telling CF4 electronegativity is higher. That is correct. Okay, I'll explain. Why CF4 electronegativity is higher? So it is fluorine. And this is CCl, chlorine. So electronegativity is depending on scope, S percentage, charge, oxidation number, and peripheral atom electronegativity. So for these two carbon atoms, S percentage, charge, oxidation number, they all are same. So they only have different peripheral atom electronegativity. So here, fluorine is more electronegative than chlorine. Therefore, fluorine is pulling more electrons towards it. And here it is also electrons are pulled, but not like fluorine. Therefore, the delta positive charge of this one is really high. Higher than this one. Okay, fluorine is more electronegative than fluorine. Therefore, delta positive charge on carbon is higher in CF4. Therefore, if the charge is higher, electronegativity is also higher. Understood? So therefore, this statement is correct. CF4 is the one having higher electronegativity. That is correct. Okay, Lama. Then look at this third statement. See, 3 equally stable resonance structures can be drawn for bicarbonate, HCO3 minus. That is wrong. So bicarbonate is having these 3 resonance structures. Let me draw them for you. Bicarbonate. The negative charge is here. And there's another resonance structure. Double bond, move to the other side. And these 2 structures are stable. These 2 are stable, no problem. But if you take the third resonance structure, which is having a double bond on the hydrogen connected oxygen, you can see that oxygen will have a positive charge. Having positive charge on oxygen and having higher charge distribution like this make this structure unstable. So then the statement tells equally stable structures are there. So C is wrong. Understood? C is wrong. Just draw the 3 resonance structures and say why this is unstable. You need to write that too. Why this is unstable. Give the reasons. There are 2 reasons. First one is having positive charge on oxygen. And the second one is higher charge separation. Higher charge separation. Okay, right. And then the last one, CH bond length of C2H2 is higher than CH bond length in C2H4. Let's see that one. C2H2. C2H2, if you draw the Lewis structure, it is this. Then C2H4, if you draw the Lewis structure, it is like this. These are ethine and ethene. You may have come across this one in O levels. But my point is, here you are having sp2 hybridization. Here you are having sp hybridization. So these carbon hydrogen bonds both are single bonds, but this is sp and s overlap. This is sp2 and s overlap. Understood? So you know that sp orbitals are shorter than sp2 orbitals in length. Okay, so therefore, this sp2s bond is longer. This one is shorter. So this statement is wrong. Understand? That statement is wrong. Statement is telling this bond is longer. Check that again. So our answers are going to be AB only. AB only. AB only. So if AB are correct, your answer is answer 1. Answer 1. Okay, now answer is answer 1. Right, so we completed ABCD questions also. So quickly, we will go through the last statements. There are 24 to 30 statement questions. This will be a small discussion, right? Because we have only 2 statements to discuss now. Let's quickly go through that. So I'll anyway go to the paper. We'll use this to explain. Right, look at the first statement of 24th question. There are some good points to learn. Any two ideal gases have the same average kinetic energies at the same temperature, right? So any two ideal gases have the same average kinetic energies at the same temperature. Now, what is the last point of the average kinetic molecular theory? Average kinetic energy is directly proportional to absolute temperature. Absolute temperature. Okay. So now students got confused. I noticed some, and some of them, some of you speak to me also. And it is not mentioning absolute temperature, but it is not required, right? Let's say there are 2 ideal gas samples, A and B. Think like this, okay? A and B. And they are at the same 25 Celsius temperature. Okay, if they are at the same temperature, it is okay to tell 25, because anyway, if you convert this into Kelvin, it is going to be same Kelvin temperature. Okay, so when you say a statement like this, it is not required to say absolute temperature. It's okay to say same temperature. Okay, but when you are comparing, let's say you are going to check the value at a different temperature, then you must say absolute. Understood? So this first statement is correct. There's no problem with this one. It is proportional to absolute temperature, but same at same temperature. Okay, so proportional to absolute temperature. Ke bar is directly proportional to absolute temperature. Absolute word is there, okay, Kelvin temperature is there, should be there. But when you say same, okay, K bar is same at same temperature. Same absolute temperature or just same temperature. Understood? So this statement is correct. Look at the next one. Last one says, the second statement says, at a given temperature, average speeds of gas molecules adjust according to their masses. That is correct. Okay, let me explain. Now let's say this gas is having, let's say, 20 relative molecular mass, and this one is having, let's say, 40 relative molecular mass. Okay, so that means molar mass is 20 and molar masses are 40. 40 and 20. Okay, and their average kinetic energies. Now, this one is having, this is heavy, no? This is heavy. Therefore, move slowly. Okay, but their average kinetic energy, say the kinetic energy is equal to half mv square, half mc square according to our derivation, right? So now take a random molecule, right? Half, if it is average, then it is Ke bar half mc squared bar. So if this one is lower, because of the higher mass, is going to be higher. Okay, if you apply the same principle for this molecule, Ke bar equal half mc square. Remember this one from derivation. If the mass is lower, speed will be higher. So they are kind of adjusted. So A gas will move faster because it is lighter. Then have a certain average kinetic energy. And this one will move slower because it is heavier. Okay, by that it will get their kinetic energies to the same exact value. If they are ideal. Ideal word must be there. Okay, so this statement, second one and the first one, both are correct. And actually second one can explain why two different ideal gases are having same average kinetic energy. So then your answer is answer 1. Isn't it, Lama? Answer is answer 1. So good question, good statement. It is actually from a past paper. And study and, memorize, remember this statement. Okay, so two different ideal gases are having same average kinetic energy because their speeds are adjusted to according to their masses. Okay, so heavier one travels slowly and lighter one travel faster. Ultimately, average kinetic energies will be same, 24. Then look at the 25th statement. Among the elements of the second period of the periodic table, the electron gain energy of nitrogen and beryllium have a positive value. Electron gain energy of nitrogen and beryllium. Okay. So what do you think? That statement is correct. Okay. So the second period elements, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. So out of these 8 elements, these 3 elements are having stable electronic configuration. So beryllium is having 2s2 stable configuration. This is 2s2 2p3 stable, half failed stable. This one is fully completed and stable, 2s2 2p6. If they are having stable electronic configurations, they will resist to accept an electron. I did explanation about electron gain energy, refer that again. So my point is, anyway, if you try to give an electron for this element, it will kind of resist this one. It says, I don't need that because it's already stable. Understand? So we have to forcefully give the electron. So the reaction is going to be endothermic or positive. Isn't it? So you are spending energy and giving that. So same thing would happen to nitrogen and neon. So from second period elements, these two are having positive electron gain energies, endothermic. Okay. So in other words, does not like to gain electrons. So this endothermic What are the other endothermic ones? Eg1 positive, first electron gain energy positive, is going to be all group 2 elements. Then all group 18 elements, and from group 15 only nitrogen. These are the electron gain energy positive elements because they are having stable configurations. Okay, so then we talk about phosphorus and everything also. Can remind that why only nitrogen? That's another question. So my point is here, the first statement is correct. Look at that again. Among the elements of the second period of the periodic table, the electron gain energy of beryllium and nitrogen have a positive value. So they didn't say only. So they didn't mention about neon, but that's okay. For these two elements, it is correct. No? And before going to the second statement thing, why is the reason? Reason is the configuration, right? They are stable configuration. The second statement is telling that configuration. Okay, so you can say the second statement is also correct. Half filled and completely filled shells are having higher stability. That is correct for the beryllium and nitrogen. So beryllium, if you draw this NS2, okay, so that shell is fully completed. And this one, NS2 fully completed, NP3 is filled half, one per each orbital. So this is also stable. So that's the reason. So first one is correct, second one is correct, and second one can explain the first one. So your answer is going to be again answer 1. Okay, so first and so 24 and 25th questions are having answer 1. Okay, answer 1. Right. And look at the next question, 26th. Boiling point of, this question is good. Okay, so most of you got this wrong. Paranitrophenol and orthonitrophenol. Now the thing is, this is coming from organic chemistry. You haven't done it yet, but still, this orthoparanitrophenol thing was there in your bonding tube. Okay, now if you have the book with you, turn to the pages that describe about hydrogen bonding. There you will find this note. Orthonitrophenol and paranitrophenol. Okay, orthonitrophenol and paranitrophenol. Right, so 26, I'll explain using the board. So it says boiling point of, first one says paranitrophenol is higher than the orthonitrophenol. It says boiling point of paranitrophenol is higher than the orthonitrophenol. Let me explain the theory part. So nitrophenol, this is paranitrophenol. Paranitrophenol means the NO2 and OH groups are there in opposite sides. This is paranitrophenol. And orthonitrophenol is the OH group and this NO2 group is adjacent to each other. This is orthonitrophenol. Okay. Orthonitrophenol. In paranitrophenol and orthonitrophenol, you can see hydrogen bonds can occur because this oxygen, so this hydrogen is connected to oxygen. See, now here the orthonitrophenol, you can see this hydrogen bond. So now this hydrogen bond occur within the molecule. So this is called intramolecular H bonds. Intramolecular H bond. So orthonitrophenol is having mainly mainly intramolecular H bonds. Intramolecular H bonds. Okay. So intramolecular H bonds is not helping to have a higher boiling point. Why? Okay, so because it is having within the molecule, boiling point is affected by intermolecular H bonds. You can say this does not help, does this not help to increase boiling point. Boiling point. So this has lesser intermolecular attractions. Intermolecular H bond. So this can form intermolecular H bond. So if there is another orthonitrophenol molecule here, it will make. But there's more chance to make within. Okay, so lesser intermolecular hydrogen bonds, therefore, boiling point will be lower. Okay, boiling point will be low. Understood. But the opposite happens for the paranitrophenol. You can see, if you have another paranitrophenol molecule, it will form very easily intermolecular H bonds. Intermolecular H bonds. Intermolecular H bonds. That means I have to draw this to the lone pair. And intermolecular H bonds, those are really powerful. I mean, they can have intermolecular H bonds between two molecules, and it is better. Therefore, this will have the opposite happens. For this explanation, opposite happens, and the boiling point will be higher. It is difficult to separate two molecules. I write that too. Here it is difficult to separate two molecules. So therefore, the boiling point will be higher. Understand? So remember, orthonitrophenol is having intramolecular H bonds mainly. Paranitrophenol is having intermolecular H bonds among molecules, between molecules. And what is responsible for the higher boiling point is this intermolecular H bonds, not the intra. Okay, remember that well. Okay, and if you check your theory book, I gave you the values of the boiling points also. It has a significance difference. As I remember, 60 or somewhere around that value in Celsius, that difference is there. Okay, so what do you think? So paranitrophenol is having higher boiling point than ortho is correct. So first statement is correct. Look at the second statement. Second statement is telling paranitrophenol forms intermolecular H bonds. Okay, correct. And orthonitrophenol forms intramolecular H bonds only. That is wrong. Paranitrophenol forms intermolecular H bonds. Okay, can understand. Orthonitrophenol, is it only making intra? No. It can make intermolecular also. The reason is it is having lesser intermolecular H bonds. See, lesser. Okay, so orthonitrophenol can also form orthonitrophenol can form small amount of intermolecular H bonds too. Okay, so telling like this is wrong. It says only, that only word is wrong. This one is wrong. Okay, so you can draw and see how it is making intermolecular H bond. Now this is your orthonitrophenol. And this is another orthonitrophenol molecule. See, it can make an intermolecular attraction. Can happen. It can form, okay? No, we can't say this not. Okay, so second statement is wrong. Answer is going to be answer 4. Sorry, not 4, 3. First one correct, second one wrong. Okay, it's a kind of a tricky statement, right? That because of that only word, it got wrong. See the answers of the first 3 questions. So I'll add this PDF after editing. Editing means adding more explanation. This is prepared for the 26 batch actually. Only few explanations are enough for them now because we have done this for years now. But for you, I need to add more explanations. Okay, so I'll update this one and this PDF and add to your group. Okay, but remember to write what I put in the board. Okay, so study that. I did a lengthy explanation for this MCQ. So 26, first statement correct. It's true that paranitrophenol is the one with higher boiling point. But the reason is having more intermolecular hydrogen than other. So orthonitrophenol can form intermolecular also, but it mainly forms intra because of the close proximity of OH and NO2 groups. Understood, Lama? Now let's move to the 27th statement. 27th statement. Ionic radius of gaseous calcium 2 plus ion. Calcium 2 plus ion is greater than the magnesium, gaseous magnesium atom. Okay, so is it correct? Now if you take this calcium electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6 and 4s2. So it has 4 energy levels. Therefore, calcium atom is larger than magnesium atom, which is magnesium is having 1s2, 2s2, 2p6, 3s2. So only 3 energy levels. Here this one is having 4 energy levels. So magnesium and calcium atoms, this is telling calcium is larger is okay. But let me show you what is the calcium ion configuration. Calcium ion electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6. So it just have only 3 energy levels and it is equivalent to, it is showing the same electronic configuration as argon. Understand? It is argon. So, and calcium 2 plus will be smaller than argon. Okay, calcium 2 plus will be smaller than argon according to this one. So across the period, radius decreases. Okay, so therefore magnesium is larger than argon. Okay, so then anyway, magnesium must be larger than calcium 2 plus. Calcium 2 plus is even smaller. Understood? So now they both have 3 energy levels. See? Therefore, the one with the more nuclear charge, more nuclear attraction, therefore radius will be lower. So telling that calcium 2 plus is larger, this one is false. Okay, it's a tricky statement, right? But anyway, if you think a little bit, you can understand, not difficult. Okay, so calcium 2 plus is smaller. Then look at the second statement. the effective nuclear charge of magnesium is greater. No, it's wrong. Effective nuclear charge is greater in calcium. Effective nuclear charge, or you can see the higher number of protons are there. So second statement you can review like this. Second one is also wrong. Okay, first one is wrong. Second one is wrong. So answer is going to be answer 5. So this is how second one is wrong. Calcium is having 20 protons. Okay, so magnesium is just having 12 protons. So therefore this one is having more nuclear charge. More nuclear charge. Okay, so nuclear charge, effective nuclear charge is nuclear charge minus sigma, or shading effect. Right? So calcium is having more, calcium 2 plus. Calcium 2 plus is having more shading effect, but still its nuclear charge is higher. Downward the group, nuclear charge increases. Effective nuclear charge is also increases. Okay, so telling that effective nuclear charge of magnesium is greater is wrong. So a good statement. Both statements are wrong. Answer is answer 5. Okay, answer is answer 5. Can understand that? Then look at the next question, number 28. It's about a very famous question. We have done this one so many times, isn't it? Huh? Ammonia and NF3 bond angle. Ammonia and NF3 bond angle. It says ammonia bond angle is higher than NF3. First one is correct. So how do we explain that? Ammonia and NF3 both are having trigonal pyramidal electron pair geometry. Sorry, shape. Tetrahedral electron pair geometry and trigonal pyramidal shape. Okay. And the difference is here. The bond electrons are more closer to the nitrogen. Therefore, I'll write bond electrons more closer to nitrogen. Therefore, more BP-BP repulsion. BP-BP repulsion is higher. Understood? So therefore, angle is also higher. So it is having 107 degree angles. But this one is having just 102 degree angles. 102 degree angle. Why? Because now the electron pairs are located away from the nitrogen. So therefore, their repulsion is not that high. Okay, so the lone pair at the top can push them towards each other. So bond angle will be decreased. So what are the reasons? The main reason for this one is electronegativity. If the electronegativity of the central atom is higher, bond angle is higher. Okay, that's the theory part. If electronegativity of central atom is higher, bond angle will be high. So now you can see in this last statement questions, you had two questions, the earlier question, you had two questions related to the bond angles. So refer that part really well. These are the tricky MCQs they can ask. Bond angle will be higher if the central atom electronegativity is high. So now let's check that reason is given for the second statement. Second statement is telling the repulsion between two lone pairs is greater than the repulsion between a lone pair and a bond pair. Okay, so what they say is not the reason we want. So second one, don't say it is wrong. Second one is correct, but it cannot explain the first statement. Therefore, answer is answer 2. So it says LP-LP repulsion is higher than BP-BP repulsion. Okay, so that's true. LP-LP repulsion is higher than LP-BP repulsion, and BP-BP repulsion is lowest. So that explanation is good. This can explain how bond angles of CH4 is higher than NH3 and water has the lowest bond angle. So in water you have LP-LP repulsions like that. So it's good for these explanations, but not for the NF3 NH3 explanation. You can refer this in your theory note. In your theory note, the first point explained was these bond angles. This was having 109.5 angle exactly, and this was having 107, and this was having 104.5. The reason for having such different bond angles are the type of the repulsion unit. Okay, that is what given as the second statement here is, but it is not explaining this point. This point in your note is a different point. Okay, so there are so many factors affecting bond angle, right? Bond length, bond like this, the repulsion type, and then you can say the electronegativity, like that. There are so many factors affecting. So study that theory area again will be valuable. So anyway, both the statements are correct, but it can't explain the first one. Answer is going to be answer 2. Okay, answer is going to be answer 2. Right. Now let's go to the question number 29. 29. Look at the first statement. Look at the first statement. Volume of an ideal gas is directly proportional to absolute temperature always. Volume of an ideal gas. 29. So according to PV equal nRT, volume is directly proportional to, but it says absolute temperature. Volume of an ideal gas is directly proportional to absolute temperature always. No. So when they say volume of an ideal gas, moles are constant. R is only anyway a constant. Volume will be proportional to absolute temperature if pressure and moles are constant. Right? But in this statement, but here pressure is not mentioned. Therefore, first statement is wrong. Okay, so you can refer Charles' law. According to Charles' law, volume is direct proportional to absolute temperature if the number of moles and the mass or the pressure is constant. Okay, so it says, it didn't say anything about pressure. So first statement is correct, wrong. Sorry, don't get misunderstand. Okay, so telling always is wrong. Not always, actually, not mentioning the pressure. Look at the second statement. Average kinetic energies of a gas molecule increases with increasing temperature. That is also correct. It doesn't say proportional. It doesn't say proportional. Second one is correct. Kinetic energy average increases with increasing temperature. But it will be directly proportional absolute temperature only. So telling directly proportional and telling increasing are two different things. That's what you need to understand. If they say directly proportional, it must say absolute temperature. Okay, if it is telling increases or something like that, it's not required, right? Anybody can understand it increases with temperature. Increasing, like I said, increasing and directly proportional are two different things, okay? Two different things. So you can say first statement is wrong, second statement is correct. It's a good question, right? These are kind of hard questions for you, Lamai, because you haven't get still a good practice, no? You are still practicing. So for 26 students, 26 A-level students, these questions are now easy, right? Because they have practiced this a lot. But now still you are in the practicing phase. So right now these questions may be difficult for you, but trust me, practice along these papers and with this process, right? While you go through the process, all these points will come to you. And once you see some interesting point, please note down those points in a different small booklet, and always keep that one close to you and read through those points. Then these points will be familiar to you. Otherwise, these good points you will see these points again in another paper. then you might get it wrong. It's a waste of your time and energy, everything. So refer these points again, right? So 29th statement, question, first one is false, it's a good point. And second one is true, that is also a good point. It's not telling proportion. Look at the last one. 30th MCQ. 30th MCQ. It says nitrogen does not form NCl5. That is correct. So this is an easy question actually. PCl5 can exist, but NCl5 does not exist. Okay, so that is correct. 30th one, first one is correct. Why? PCl5 is there, but NCl5, you can't draw NCl5. The reason is nitrogen cannot form more than 4 bonds. Nitrogen, or you can say second period elements. Second period elements cannot keep more than 8 electrons in valence shell. Because in the second sub-energy level, second energy level, it can keep the maximum 8 electrons. So this is called octet rule. Octet rule, a very famous rule once we draw Lewis structures, remember. And in other words, remember this point, CNO, carbon, nitrogen, oxygen must follow octet. We use this theory point when we are drawing resonance structures. Okay, so these are actually derivations of this main theory. Okay, second pair elements can't keep more than 8 electrons. So the maximum number of bonds is 4. Maximum number of bonds is 4. So why that has happened? Why that has happened? Why this octet rule is there? Okay, the reason is this, but my point is why PCl5 could do this one? Phosphorus, why it could do this one? Phosphorus can keep more than 4 electrons, but PCl5 exists. Why? Nitrogen NCl5 does not exist, but PCl5 exists. Why? The reason is if you take phosphorus electronic configuration, it is 1s2, 2s2, 2p6, 3s2, 3p3. Right? So now, in the ground state, this is the way those electrons are arranged. Okay. But you have to notice it has a 3D sub-energy level which is empty. Right? So when it needs to make 5 bonds, what it will do? It will quickly push 1 electron to 3D. Now check. Now here you have only 1 electron. And in 3p3 you have 1 electron per each. And from 3D 5 orbitals. In the first one you have 1 electron. So now you have 5 unpaired orbitals. So these orbitals will hybridize to form sp3d hybridization. So therefore it can make 5 bonds. So now you can see why nitrogen couldn't do this one. It doesn't have any d orbitals, right? Because in second energy level, you have only S and P sub-energy levels, not the D sub-energy. So maximum electron holding capacity is 8 for the second energy level. But if you come to the third energy level, fourth energy level, and so on, they will have S, P, D, and F like that, everything. So then they can keep more than 8 electrons, which means it can make more than 4 bonds, 5, 6, like that, octahedral, trigonal bipyramidal. Those geometries are resulted by this hybridization. This hybridization is not there for your syllabus. I just wrote it for explanation only. But just know, phosphorus could make 5 bonds because it is having d orbitals. Now check your second statement. Electronic configuration of nitrogen can't expand beyond octet rule because it doesn't have d orbital. That's a correct statement and it explains the first statement. Okay, that's the proper explanation. Study these points. All these questions are really good. Okay, so even for this paper, if you are right now, since you are practicing, still getting 15 MCQs correct, 12 MCQs correct, still fine with me. Because I know at some point you will get 20 out of 30. With this practice, if you go in this path forward. Okay, so remember to write good reviews and study with them, repeat them. That's your problem. You are not repeating. I said that all several times. So study and repeat. Okay. Right, so this is it for the 30 MCQs. So we did very extensive discussions for the first 15 MCQs and a brief kind of necessary discussions for the last 15 MCQs. Right, now so the 30 MCQs are completed. So that's it for today. And complete your review. I'm going to check that one in the class. I'll mark it, go through it briefly and tell you whether it is anything missing. Right, so complete it and do this paper once again this month. This week you can try, right? Upcoming week, I'll tell a date and practice the paper again. Do the paper again. Okay. So right, have a good day, Lama. Study well. Right. If you have further doubts regarding the 15 the questions we discussed today, you can reach me. I'll explain. And yeah. Okay. Have a good day. Study well. Goodbye.